good evening, and thank you all for coming tonight. This is the second night in our family learning series it's a year-long series. Pam Allen was here earlier this month. And on your way out, if you haven't gotten one already, there's a sheet with all the rest of the series on the back table. So I'm Heather Haynes. I'm the elementary math specialist for Acton-Boxborough, and I'm pleased to be able to introduce to you this evening our two speakers, Grace Kelemanik and Amy Lucenta. Grace and Amy work for Boston Teacher Residency, and they also work with districts around the state on helping teachers to implement the elementary mathematics practices. This summer, the teachers in Acton and Boxborough were lucky to be able to work with them. Grace is a former mathematics teacher. She worked at City on the Hill Public Charter School, and she was also a former project director at the Educational Development Center. Amy's been a math educator in public and private schools for about 20 years. After she spent some time teaching middle school and high school mathematics, she served as the elementary mathematics coach in the Newton Public Schools. So please join me in welcoming Grace and Amy. Thanks for coming out tonight. This is a gorgeous fall night to spend doing a little math together. It'll be a fun, hopefully a fun evening. Just before we get started, we wanted to get a sense of who you guys are. Can we just see a little show of hands if you have children in kindergarten or first grade? Third of the room. And second or third? Ooh. And 4 through 6? And I think we have some overlap now, and older than 6th grade. Wow, excellent, great range. And perfect, because a lot of the math we're going to talk about today spans many grade levels. Have you had a chance to read the quote at the beginning here? We're going to come back to this. It's interesting to note, in addition to the fact that we don't know what kinds of jobs and what kinds of technologies and what kinds of problems we're preparing kids to work with and solve and think about in the future. In addition, the U.S. Department of Labor, I think this was a couple years ago, reported that 65% of today's grade school children will end up at jobs that have not yet been invented. So we'll kind of unpack what that means for us and our children in schools today. So that's us. We're going to spend some time with you tonight. Does anyone tweet in here? Tweet, Twitter? Yeah. We're kind of new at this, but those are our Twitter handles, and we just heard Acton-Boxborough's AB, tell me it?
At AB Learns.
At AB Learns. So if you feel like tweeting anything out that you're learning or thinking about tonight, those are some Twitter handles to tag, or whatever you call them on Twitter. So in the next, between now and 8:30, we're going to talk about some of the need for shifts in math learning for our kids. We're going to experience some math to bring the shifts to life for you, so you can get a sense of what it feels like to think in the ways that your kids are being asked to think in, and then discuss the implications for your children. And if there's any point that you want us to stop and clarify, or either the language or the mathematics that we're talking about, please feel free to do this. We want this to be, it's your night to learn a lot, so interactive. Good? Logistics. I think I might not be the one to give you good directions here. Restrooms are, that way? I went that way, so apparently there are closer ones.
All the way at the end of the hall.
Go out and take a right. Good. So let's talk about the math that we know that kids need to learn and understand, and the math
compared to maybe what we think the math they need to know and understand is, and then where we're headed with it. What we know is that math requires skills, mathematical skills, and kids absolutely need to learn those skills, and they absolutely need to learn mathematical procedures. And if we stop there, we in essence give kids the tools that they could get in their handheld device, whatever that device will be by the time they're in high school or college, if we stop at the skills and procedures. So we know that mathematical concepts are also equally important, that without conceptual understanding, there's really not much point to learning mathematics as a domain. So we also argue, and we'll talk more about this tonight, that mathematical thinking is truly at the heart of what we hope for our students to learn, to develop, and be prepared to do as they move through the grades, through elementary school and into middle school. And the mathematical thinking actually ties the skills, concepts, and procedures together. It's the glue of them. It's the reason behind them. It's the reason the skills and concepts and procedures developed was from that mathematical thinking in the first place. So tonight we'll really make sense of all of that and what it means for us. How many of you have heard of Common Core state standards? Ooh, very, very good. So Common Core state standards came out a few years back, and in 2011, Massachusetts rewrote their standards to integrate the Common Core state standards. So Massachusetts follows the Massachusetts framework, but it's written with Common Core state standards. So you'll hear both talked about. In those standards, there are standards for mathematical content, and Acton-Boxborough has been working for a number of years aligning their mathematical content to the 2011 frameworks. There were a couple of years that we had to transition over to the new standards, and Acton-Boxborough's done the heavy lifting of that alignment of content standards. In addition to content standards, there are standards for mathematical practice. So the content standards are described at each grade level. In second grade, there are content standards for second grade that are different from those in third grade. And then there are standards for mathematical practice, mathematical thinking, mathematical habits of mind, the way that mathematicians think mathematically. And those actually run from pre-K through 12, K through 12. They're the same standards all the way through all of the grade levels, so they're a little bit different. And Acton-Boxborough over the past 3 years, sorry, I had to think about that. We were here for them, it just feels like it couldn't have been that long, it is. Has been working to integrate the mathematical practice standards into their curriculum and into the classrooms and into the development of student thinking. So that's the good news. You guys are in a district that's really taking this head on and understanding that what they need to do and we need to do is teach the thinking. Teach the mathematical thinking that's described in the standards for math practice. Has anyone seen the standards for math practice before? Oh, I finally got you. Good, good. So now everyone will have seen them. I'm actually just going to give you about a minute to read through this list of 8 standards for mathematical practice. So as I look around, there are a couple of you that are alone at a table. If you could join up with another table, if you're at a table, move to a table where there's just a single person. Talk to your table mate. What are you thinking when you read these? What is it making you think of? And take about 45 seconds. Go. Let's put on thinking.
reasonable, pretty completely, I guess.
All right, let's pull back together. So, you were quietly talking about it, and I heard one thing that I want to first address in the full group. These slides are all going to be available on the Acton Boxborough website, as is this video. So no worries, you don't need to write everything down, you don't need to take pictures of every slide. Of course, write something down if you want to, feel free to, but don't feel like you have to capture everything. You'll be able to dig back into it. So a couple things I heard around the room as I walked around was that it's kind of technical language and that there's not a lot of description here. And so these 8 standards for mathematical practice are also accompanied by a 1-paragraph description of each of them. And if you recall, these span all of the grade levels. So there's a lot of unpacking to do and making sense of them and what they look like at different grade levels and what they look like in the classroom. And that's the work that Acton Boxborough has taken on. Did anyone notice anything about the color?
Oh, the red words?
Yeah, the red words. Did you notice anything about the red words?
Mostly words.
And what did you talk about why you thought that might be?
Active process.
Yep. Verbs, because that puts you into the process, and they're actively engaging math practices, describing how how mathematicians think, and then our job is to develop that thinking in students. So the question is, how do students actually learn to think like mathematicians? And our response is they learn to think like mathematicians in all the same ways they learn in general. All the same ways they learn skills and procedures. They name it. They name the what of what they're learning. They practice it. They practice what they're learning, and they apply it. So in this case, they name the thinking. We need to be able to talk about what it means to think in these ways. We need to be able to practice that thinking in groups, with each other, alone, independently, at home, in school, in different areas, and then apply it in new areas, problems that we haven't seen before, but apply those ways of thinking to problems that we haven't previously seen. So we thought it might be really helpful to bring that to life for you and take one of the standards for math practice 7, look for and make use of structure, and actually do that together tonight. So to name the thinking, practice the thinking, and then talk about applying the thinking. So Grace is gonna take us through that.
So great. I'm going to do math with you. I get the fun part. Amy talks about math. We actually get to do it with you, which is good. So for about the next 15 or 20 minutes, you guys get to be math doers and experience math. And then when we're done, we'll peel back and kind of talk about what that experience was and what the mathematical thinking was that, in theory, you were working on and developing. So we should get started. So we're going to do this instructional activity called Contemplate and Calculate. And what that means is we're going to practice looking for shortcuts, mathematical shortcuts. And why we want to do that? Because we want to learn to think like mathematicians. Mathematicians use what they know about mathematical structure. And when I say mathematical structure, what I mean is the way numbers work, the way you can take them apart and put them together, the way operations work, addition, subtraction, multiplication, division, rules like you can add in either direction. 3 plus 5 is 8, and 5 plus 3 is 8. But you can't subtract in both directions and get the same answer. 3 minus 5 is not the same as 5 minus 3. So those rules that help us work with numbers and shapes. So we want to leverage those. So how are we going to do this? We're going to do 4 steps. We're going to start by looking at something, and I didn't tell you what that is yet. You're going to have a little bit of time to look at something and just notice what you think is significant about it. Just train your eye to look like a mathematician. And then we're going to use our noticing, working together with a partner to find a calculation shortcut. We're going to share our shortcuts, study them, and then we're going to reflect on our learning. So first step is the noticing. So in about 10 seconds, Amy is going to project for a very short amount of time, maybe 3 or 4 seconds, an image. And all you need to do is look at the image and think about, what do you notice about it? You don't have to memorize it, you don't have to do anything with it except what you think is important about this image. What stands out for you? Okay, is everybody looking? Okay. Oh, yes, and Amy's giving me the no pencil, that upper right-hand corner. It's supposed to remind me to say no pencils. You don't need to write it down or do anything. Just, in fact, you don't really need your pencils for any of this. So just put your pencils down and take a look. You guys looking? Good, good. Great. So, turn to your partner, your shoulder buddy, the people at your table, and share what you noticed. And if it's helpful, you can start by saying, I noticed, or turn to your partner and say, what did you notice? Come back into the full group. Does anybody know the answer to the question?
Not until you tell us if we're right or wrong.
Well, there was no question, so if you knew the answer, you're good. We purposely didn't put a question, we just want you to notice. So, someone from this table, what did you notice?
Well, we said bubbles.
Bubbles.
And that if you were to switch them up, it's almost a mirror image.
Huh, like this, almost a mirror image, so there's the symmetry there, some sort of mirror image. One of the young ladies here in this table, in the pink, what did you notice?
Circles, and it kind of looks like some things were missing, and also the circles were formed like a square,
So you noticed some circles.
and it was shaped like a series of some that was missing.
Looked like missing pieces, or something was missing.
And it, like the circles were formed like in a 90 degree.
Like in 90 degrees, and did you say, did I hear rectangle or square?
Square.
A square, 90 degrees, something about a square. That's a lot. So we're noticing some things about what the object's made of. We're noticing things about how it's laid out. We're noticing shape, our eyes picking up shape. Great. So for the next part, here's what's going to happen. We're going to ask you to, what we like to call a quick count. Come up with a way to quickly count all those bubbles and circles in your head without having to count each and every one of them. So take a look at these noticings and pick one that you think might be helpful. And we're going to put the problem back up. And with the partner, talk with the partner about how you would quickly count, a shortcut for quickly counting all the circles or bubbles. Okay? So, a couple of these that we can draw on and take a look at. So what we're going to do now is share out some of the shortcuts. And what I'd like to do, the way in which I'd like for us to share, is we'll ask for a presenter to start and explain their shortcut. But what I'd really like for you to do is start with, what is it that you noticed? And so therefore, what did you do?
Can I just make an observation here? You're missing one up there on the board.
One's on the top here.
Yeah.
One of the things you
The
noticed
flange.
was we were missing.
Oh, sorry, did I?
Oh. Oh. There we go. It's not much longer. Okay. Thank you. Look at that.
Sorry.
Or something that you knew, so then what you did. Okay? And everybody else who's listening, you're the audience. Your job is to really listen for what it was they initially noticed, and then how they use that noticing to develop a shortcut, a counting shortcut strategy. Yeah? We start in the way back. Yeah? You can just tell me, nice and loud, what did you notice?
So, you notice that like she said, there were these bubbles or dots, and then there was the symmetry. So we counted the number of rows and columns for the completed ones, and then we have. So what we did was we just counted the number of rows in one side, and then we found out that there were 4 of them laid out in that specific row.
So 4 rows?
No, four dots in each row.
4 dots in each row, okay, yep.
And then the 3 rows, which is like 12, and then the symmetry, the opposite is going to be 12 as well. And there were 3 of them which were standalone, so we just added them.
Okay. Good, good. Someone in the room, please be brave enough to stand up and rephrase what the back table was paying attention to, what they noticed, and what they did with that noticing.
Okay, I'm just going to try.
Yeah.
So what I observed and what I thought is like, that's how I was thinking. So basically when it came up, the first picture which came up, it was more like symmetry. And my first take was like it is doubling up. And one is like half of it, and one is like half of it, and there is some additional to it. That's the first thing I noticed. Well, there were bubbles and all, but okay. Then the second, when I was counting it, I tried with the groups. So it's basically the logic of groups. So the groups we are forming is 4 into 3, it's 12 done, 12 here, 1 added to there, and 1 is in the common. That's basically what we were saying it shows.
So seeing the symmetry of the
Yes.
3 groups with 4 in each row, or what you said was 4 groups of 3, and then there are 3 left over.
Yes.
So 12 times 2 plus the 3.
Yes.
Great. Awesome. Good, good. Who had a shortcut that looked a little different than this? Yeah.
So for me, it was, my eyes were drawn immediately to the spurs and the fulcrum. That was just how I saw it. So I immediately looked at the
Is this the
3
fulcrum?
points. Yep, exactly, right? So the 3 points that were distinct. And it was, so I first looked at the spurs, or
Yeah.
the flanges.
Yeah.
And this, as soon as I spotted those 3, it was easy to notice that the rest were just groups of 12.
So as soon as you noticed those,
Yeah.
then you saw this is a group of 12 and this is a group of 12.
Yeah.
How did you see
I
that?
don't know. It's just what my eyes were drawn to.
And that just was 12 to you.
Yeah.
We're going to talk a little bit about the word for that. In kindergarten, kids learn to do, to just notice number. Yep. Did anybody else chunk this object differently? Yep.
So what I see is that we saw the 3 leftovers. If you move the 2 leftover bubbles,
We're going to put
the 2 leftover bubbles down to the rectangle part, and you're going to have a 5 by 3.
Yep.
And you're going to have a 4 by 3.
So you want to move
The 2 leftovers.
these 2 leftovers
Yes. And down to, yes, here.
down to here.
So you're going to have one 5 by 3 and another one 4 by 3.
So that gives us 5 by 3. And this gives us a 4 by 3. Yeah, 15 and 12, put them together. Great. So one of the things you were paying attention to, like the gentleman beforehand, was sort of these outliers. The pieces that were lingering out, and then you moved them to another place and created a new rectangle with different dimensions and counted that quickly. Great. Good, good. Let's move on. So, let's take a minute and, does anybody remember why we were doing this in the first place? This whole activity, this contemplate, then calculate?
To think.
To think.
Look for structure.
To look for structure. To think like mathematicians by looking for shortcuts, using mathematical structure to do that. So, by using what we noticed about that shape and make connections, change the form of it, chunk it up into pieces that we could work with and leverage to quickly count. So what I would love for you to do now is to reflect on what you learned about looking for shortcuts. Because if we're done tonight, and the thing that you walk out of here knowing is that there were 15 and 12 is 27 dots, and if that's what you take away from this activity, that there were 27 dots, then I just wasted your time. Right? You've got to walk away from this math doing with something that's more valuable, with something that's more useful to you in the future when you bump up against another problem. So what is it that you learned about looking for shortcuts that you might be able to use in the future? And I'd like you to choose one of these sentence frames to help you focus your reflection. To find a counting shortcut, look for. Or noticing blank helps me count quickly because. Or knowing blank comes in handy when you're quick counting because. So take 30 seconds, and you can even write the sentence down on a piece of paper, but complete the sentence on your own. Okay, great. Can I pull you back together, please? Awesome. Who would like to share something you're taking away that you learned about looking for shortcuts, thinking like a mathematician? Yes?
Noticing groups help count quickly because they got me the answer faster.
So noticing groups. And what do you mean by groups?
Like the columns that had, the 4 or the 3.
So columns and rows, that helps you count more quickly? Yep. Someone taking away something different. Yes?
And looking for familiar patterns that I know how to calculate, like smaller patterns.
Looking for familiar patterns, and were they, can you say a little bit about the pattern?
Like for example, in the case of the rectangle,
Uh-huh.
and that I know how to calculate that small rectangle, and then I know then therefore how to calculate the whole.
And then you can put together. Yep. So looking for familiar patterns or familiar shapes, friendly shapes that you know how to work with, that you can leverage to count quickly. Yep. Another takeaway?
If you know multiplication, you can use those patterns to quickly count.
Ah, so you might look for a rectangle because you know you can use multiplication to get the total number of items in that array or the area of that rectangle. Yep. Good.
So I thought the word structure was really good because structure encompasses whether it's commonalities or differences, and that's really what it boils down to is whether, and to use his word, which is excellent, patterns, right? So within structure there's patterns, and patterns are patterns of commonalities or differences. And that's, I think, aside from the multiplication, which I think obviously leveraging, I think the quickest thing to do is look at the structure, patterns. And same or different.
So one of the things you're looking for is what's the same and what's different. And that was, if I recall, you were the person who was talking about the outliers, kind of the different things.
Right.
Like these 3 different things, and then those 2 chunks that were the same, kind of leveraging them. So your eyes seeing those pieces. Great. Awesome. So we're going to go ahead and post this list up on the wall. And then when you come in tomorrow, we'll do another contemplate and calculate. And we'll be reminded of the things that it's important to look for in mathematics, about how numbers get put together and taken apart, and how shapes can be changed and leveraged. In this case, we quickly counted, but tomorrow we might be doing something else. But we'll continue to use the way we think structurally. Yeah, I'll slide that over.
By the way, was that done on purpose? A-B-A? Instead of
Yeah,
A.
Acton, Boxborough, Acton. The next one was Boxborough again.
Yeah.
You do numbers, not letters. all of our errors, I'm noticing.
He's looking for things that are the same and different.
Structure.
So, yeah, so one of the, yep.
So we started with this triangle, skills and procedures, thought about conceptual understanding, and at the heart of all of this is the mathematical thinking that ties it all together. So Grace just walked you through a routine to name the mathematical thinking. And I'm curious, what is the mathematical thinking that we just named? Is anyone ready to name it? We usually run through this 2 or 3 times before we do it, but the mathematical thinking at the heart of it doesn't just sit in one grade level. So in some ways, it's a hard question to ask you, one, because we ran through it once, but also because you may be thinking about a whole lot of content right now. And this same activity actually can generate structural thinking in many different content areas. So we want to spend a little time walking through the concepts that we could be developing, the math content we could be developing with this kind of thinking, that we look for groups that are the same or different, and we look for familiar patterns or shapes or familiar organization. We look for rectangles for dimensions to multiply. We leverage multiplication in different contexts and ask ourselves what's the same and what's different. And that happens throughout the grades in many different ways. So here's a little walkthrough, like through the years. We should have a little music.
The years. Oh wait.
I want you to keep going.
I don't know the rest of it.
So those of you talking earlier that said you had a kindergartner, in kindergarten and first grade, in Acton Boxborough schools, children are learning to subitize. Does anyone know what subitizing is, besides having? Oh!
The man in the back, because he subitized today.
Subitize. Anyone? Yeah, a lot of teachers don't either because it's a technical word, but what's more important is that we know what it means, and what it means is to instantly know quantity. So to look at a die, the face of a die, and see 6 and know it's 6, and connect the quantity of 6 to the numeral of 6. So instantly knowing quantity is something kids work on. That's why they play games like Connect 4, where you drop the checkers in, or Othello with the black and white chips, or any of those dominoes, dot games build students' capacity to learn to subitize, and it's a necessary developmental milestone before they go into other things. So it's not just for efficiency, there's mathematical thinking that happens that then gets built on. So we could use this activity to develop subitizing in young children, or to review subitizing or strengthen it in older children. And we could also mine it for the structural thinking. So what groups did you see? What did you pay attention to that allowed you to see those groups? So in the example, I think this green one started with 3 rows with 4 dots in each row. I chunked those 3 rows together, I grouped them, and I saw 4 in each row. So that's subitizing, groups of 3, and then, groups of 4 and 3 of them. Some of you subitize this big thing, 4 by 3, which is actually kind of hard to subitize. That's big and it's not a familiar arrangement of shapes or images. So what you pay attention to is different. I'm looking for rows because that helps me subitize. I'm looking for rectangles because I can chunk that. So that might be content early on. As kids move through the grades, they may be working on skip counting to transition from individual quantities to putting quantities together and thinking about what it means to add onto numbers. So they may be counting by 3s, 3, 6, 9, 12 on a number line or on a 100 grid. And so this actually gives them an application of that, and they're connecting the visual. They're connecting these rows of 3 to skip counting by threes. They may be transitioning into multiplication and talking about arrays and really looking for arrays in figures that they see and connecting that understanding of multiplication to the visual model for multiplication, going from the repeated addition toward the array model. And when they continue on that trajectory through the array model, they enter into area. So a 3x4 array, a 3x4 open array, measuring the area of that green array rather than counting the dots of it. And then this young lady in the pink talked about a square with missing parts. And once we're good at seeing those shapes and those figures that aren't actually there, but that'll help us, so we can look for rectangles. And we can find rectangles. I don't know if you can see the shaded part in here, the center. Can someone describe it to me? I can't see it right now. What does it look like?
Almost like one on top of the other.
Looks like one on top of the other? One what?
Square.
One square on top of another? Okay. What else? Can someone add to that?
It's a 4x4 square with one square taken out of two different corners.
So you see a square with one smaller one, a 4x4 square with one smaller square taken out of two corners. Okay. So you looked for a square, but it wasn't really there. And you were able to then leverage that noticing, because those are things you look for structurally, to now maybe use that fact to find the area of this quickly. 4x4 minus 2. That's a whole lot easier than counting each individual square unit. And we have this one in the room too. Similar, different. Take a look at this. I'll tell you this, the top pink and yellow is actually the same pink and yellow over there. And it's moving over to form this bottom figure. So when I look for things that are the same, maybe it's the same dimension, I notice there are rows of 3 and rows of 3, I can put those together. And oh, I know enough about area and counting to know that I can move things and it won't change the area. So I can change the form of that visual, and when I look to change the form, I'm going to look to change it into something like a rectangle with maybe a missing part or an extra part. So the content through the grades is clear, that we can use this for multiple points throughout. I mean, we actually just went from kindergarten through 8th grade in content. Grace and I were talking about how actually we think there's something about area under a curve here, that we're approximating an area. We do that in calculus. So there's thinking there that transcends the grades, and naming that thinking is what we're talking about in terms of the shifts that Common Core is asking, Common Core and the Mass state standards are asking us to do. So the concepts go through, and it's the thinking that glues those concepts together. So students start to see that, oh, when we subitized in kindergarten, it's really similar to when we're building arrays in 3rd grade, and ooh, now we're transforming rectangles and almost rectangles. It's kind of like when we subitized in kindergarten. Then they're not learning something brand new every year, because that kind of thinking stays with them and carries with them. And that kind of thinking, we like to use this language for it. I don't know if you remember earlier we said, how do kids learn it? We name it, we practice it, and we apply it. So we name it. We talk about chunks, looking for friendly chunks. We talk about changing the form of expressions, of visuals, of equations, of figures. We talk about connecting to mathematics we know, connecting to multiplication, connecting counting to area, and making use of those connections. I just want to pause for a minute to see if there are questions in the room. Because I know we're kind of going through a lot of stuff. So let's go back to that. Skills, procedures, concepts. It's actually the mathematical thinking that sits in the center that drives the skills, procedures, concepts that we learn. I mean, the number system came about because people were thinking and reasoning mathematically, and they needed to develop the number system further. So we started with whole numbers and built onto it because the thinking and reasoning required it. And then we just started learning the output of that, what we do with numbers and operation, and we kind of abandoned a lot of the thinking that was underneath that. So now our new state standards and our new curriculum and Active Foxborough as a district leverages the progression of ideas and progression of thinking to develop it in students. So leverages the way math progresses, the way the content progresses, to develop that thinking in students. So, one major shift your children will experience is that they'll begin to see and understand the interconnectedness of mathematics. So, do any of your kids say math doesn't make sense? You can admit to it. I think only someone, maybe a shy two. Many students will say math doesn't make sense. They don't see the connection between what they did yesterday and what they're doing tomorrow, and they feel like every new unit is a new idea and a new topic. And it's very fragmented from their perspective, and there's a reason for that. We've been teaching it that way. We've been teaching it, and I say we, the bigger we. So the shift here is for them to see the mathematics as interconnected. Because if we can connect it to what's already in our long-term memory that we understand, it's a whole lot easier to synthesize that idea, that new idea. And if we're synthesizing the ideas, we're seeing mathematics as a content area that makes sense, that's interconnected, and therefore is doable with effort, because it doesn't seem made up. So let's take another look at this. I'm going to ask you guys now to think like a second grader. And when I say think like a second grader, think like a second grader who follows rules really well. Okay, like he or she knows the rules really well and follows them, just to play along. And with that second grader in mind, how would that second grader describe how to add 47 and 12? Turn to your table mate and share how they might describe it. So I asked Eunice to start us off here with putting on this second grader hat. You're a second grader who knows rules really well. And maybe I should have added, doesn't see math as interconnected. So Eunice, how might that second grader add 47 and 12, or tell me how to add it?
Miss, you need to write it like a math problem.
Oh, right.
So
what does that look like?
You need to put 47 on top.
Uh-huh.
And you need to put the 1 under the 4 and the 2 under the 7.
How do I know to put them there?
Oh, because you taught us that.
Because I taught you. You're right, I did. Remember I taught you guys? We line them up to the right.
Right.
Exactly. So we can actually put a ruler here. They're lined up. And now does it look like a math problem?
Yes.
Excellent. We got another one for you, but now you need to think like a fourth grader. Follow the rules for addition and add these two numbers.
That's beyond my...
Do those rules work? Let me just go over them again. I line them up all the way to the right. I make it look like a math problem. I line it up all the way to the right. And so, just like if I had a ruler here, I put my numbers there, and I add. Because those are the rules for addition, right?
That's not how you add decimals.
What? No, that's how I learned to add.
Or there's a different rule for decimals.
Oh. What's the rule I have to follow for decimals? Oh. What do you think? Line up the decimal point. There's only one.
No, but like, you have to add one and then like
Add the decimal point, and by add zeros, Adding 0, that doesn't do anything to the number. It doesn't. When I add 0, it's just still the number.
It helps you.
The line?
0's over here. All right. So you guys get the idea, right? The rules just changed on me. I learned addition really well in 2nd grade. And I got to 4th grade and I had to throw those rules out, learn a different way to add. Oh. Then I go to 5th grade. Because I know how to add decimals. Now I have to add fractions. So I get it. I put a decimal point in, right? Where do I put the decimal point in this? Oh, good God, I don't know. Math makes no sense, right? Well, let's flip that on its head. What if we looked at this problem and said 47 plus 12, which I totally heard some of you guys talking about, saying, well, 47 and 12, I want to add the 1s to the 1s, so I can add 7 and 2. And I want to add the 10s to the 10s, so I can add 40 plus 10. So 40 plus 10 is 50. And 7 plus 2 is 9. 50 plus 9 is 59. So I add the 1s to the 1s and the 10s to the 10s. Beautiful. Let's go to 4th grade. Does that work still? Can I add the 1s to the 1s and the 10s to the 10s and the 10ths to the 10ths and the thousandths to the thousandths and the 10,000s to the 10,000s? I'm seeing a lot of nodding. The rules still work. That's a structural way of looking at addition. Looking at the way addition behaves versus looking at the rules for addition that we lay on top of how addition behaves. If we learn how addition behaves, the rules follow suit, rather than learning the rules first. Then we get to fractions. Well, I know I need to add likes to likes, and I have quarters and halves. So I can't add those yet. I need to look to see if I can change the form of those to make them be likes. So is there a way I can rewrite and change the form of quarters and halves so that they can talk to each other?
You find a common denominator,
Uh-huh.
and then you half equals to 2/4.
So you can change the form of 1/2 to 2/4. If I have 2/4, can I add it to 1/4? Because those are like terms, 2/4 and 1/4. So adding same to same, like units to like units, leads us to like terms, and suddenly we just went from like 1st and 2nd grade to algebra with the way addition behaves. So when students learn common underlying structure, addition actually behaves the same way every year, rather than throwing it out and learning the new rules. When we go ahead to algebra, we can look at 3x and 7x, and those are both describing x. We have 3 x's and 7 x's, or we have 3 chunks of x plus 2 and 7 chunks of x plus 2. 3x plus 2's and 7x plus 2's. We can add those. They're like terms. And addition makes sense, right? It's the same addition we've been learning all along. In fact, many of us as adults learn to think in these ways, and by in these ways, I mean by using structural thinking. Take a look at this problem. How much change would you receive if you purchase an item that costs $2.73 and you pay $3? And slow yourself down to think about how you're thinking about it. And go ahead and talk with a neighbor. How would you figure out how much change you get? So I wish you guys had big name tags on in the orange jacket. Can you share how you were thinking about it?
Sort of like the adding like to like, but your goal is $3, or you can get rid of the decimal point, just make 300 pennies. Got 273. You need to, how many do you need to add to 273 to get the $3? You need 7 1s and 2 10s.
That's complicated. Where's my head? Okay.
Yeah. So you thought of $3 as 300. And I appreciate the fact that you didn't say I can ignore the decimal point. Because you didn't ignore it. That's 300, like 300 pennies.
Yeah.
We can actually name it 300. We can change the form of it and think about how much it would take to get from 273 to 300.
Yeah.
So you added on to 273 to get to 300?
Mm-hmm.
That's weird. I thought this was a subtraction problem.
But that's the way they teach cashiers to add change.
Oh. That's how they used to teach cashiers. So are you saying that's no different than the math that people learned years ago? So like this new math actually isn't so new? It's actually what we use in everyday life. We use structure because we as adults understand the number system so well. We can toggle between hundredths and hundreds and change the form and change it back. We can use what we know about whole numbers to work in decimals. We can, there was one other thing I heard in your thinking that I just forgot. We can add up even though we're subtracting because we know the relationship between addition and subtraction. We're using how number and operations work, the rules, as Grace described earlier, about addition and subtraction. Can we get one more strategy? I heard someone talking about quarters. Yeah.
So since it's money, I would break it down into quarters. I automatically know those numbers, so then 275, you have a quarter, and left over is just 2 cents.
Can you say that again after you looked for quarters? What did you?
275 is the nearest in groupings of quarters. So that gives you a 25-cent difference. From 275 to 273 is just 2 cents. And so then,
Okay. So using those friendly benchmarks, and in the money system, quarters is our friendly benchmark. In our number system, quarters also are friendly, and place values also steers us toward friendly.
Kind of like squares and rectangles
Oh,
are friendly.
look at that.
I know what to look for.
Looking for groups of quarters, familiar pattern shapes or numbers, rectangles, or a shape or an amount that's friendly. Super cool.
We should do another one.
You ready for another? You guys got so good at addition through the first one with the dots. Now you've totally mastered subtraction completely in 5 minutes. And so what's next? Ooh. How would you multiply 97 times 5? I'm going to give you a minute individually. All right, let's pull back together. I can tell it's time to come back together. So, who in the room is willing to share their strategy to multiply 97 times 5? And we'll first just talk about the strategy. And then we'll dig deeper and talk about the structural thinking embedded in it. Yeah, go for it.
I split 97 into 90 plus 7. And then I did 90 times 5. And then added 7 times 5 to that.
Can she do that? Can she do that?
I did a little different. I didn't.
Well, I want to hear about your work.
Oh,
I definitely do, but I first want to know if that's legal to do. Oh, good. Oh, good. You told me it was legal to do. We're done. Why is it legal? Like, this is multiplication and she's telling me to add.
She's chunking.
Ooh, she's chunking what?
tens and ones.
Oh. She's chunking tens and ones. She's breaking that 97 apart into tens and ones. But did she multiply all of the 97 times 5? You sure? So she took that 97 and instead of having it be 1 unit of length 97, she broke it into, say, 90 and 7. and multiplied the whole thing by 5? So the 90 times 5 is here, 7 times 5 is here. Now I have a challenge for you. Let's play a little ESP. What's her name?
Emily?
Emily. What was going on in Emily's head? What did she pay attention to that helped her chunk in that way? What do you think she paid attention to? We don't know. We'll find out afterward if we were right or wrong. But what do you think she paid attention to that helped her think in that way?
The 5.
The 5? Why the 5?
Just seems like it's telling you when this number should be multiplied by this number.
Uh-huh. That's when doing the multiplying.
Thought she was looking at the tens.
So thinking, is there a way to break apart the 10s and the 1s?
Simplify the problem so that you find an easier problem to solve.
Say that again.
Simplify the problem to find an easier problem to solve.
Uh-huh. So what's easier about this? Because it doesn't really look simpler, right? In the middle, it's like an omelet. It's got to get messy before it's good again. So,
Yeah, what's simple is that for the numbers times number simpler than the two digits times value.
So when I then go multiply 90 times 5, I can do that mentally. And when I go multiply 7 times 5, I can do that mentally. I couldn't have multiplied 97 times 5 as it was mentally. Okay, I buy that. So how does that resonate with how you're thinking?
It's pretty accurate. I was like, not distributing property, but like splitting that up and then whatever they called it back in the day.
7th grade, distributive property.
So what you're now saying is that when you multiply 2-digit number by 1-digit number, you're implicitly using the distributive property? Oh. So when you learn distributive property, it's helpful to connect to the multiplication you learned in whole number and then transfer it to variable.
I teach that maybe would be proud.
And that's the kind of structure through the years that we're talking about. Woo, super cool. Was there another strategy in the room? Who would like to share it?
Oh, back in the back
In
corner.
the back corner, yeah. I forgot, sorry.
Similar idea, like it's easier to kind of add more zeros to make it simple. I did like 100 minus 3 times 5.
Great. 100 minus 3 was 97 times 5, which is 2 digits by 1 digit, and you changed it to 100 minus 3 times 5? Okay.
So the idea to split that way is like you go to the nearest 10, so, and then here the nearest 10 is 100. That way you don't end up with a bigger number, like 7 times 5 is there, but if it's 99 times 5, then doing that way is better than way.
So you went bigger. You did 100 times 5. So then, what did you have to do? You said you went 100 times 5?
Minus 3. Minus 3 times 5.
What did you take off then to compensate for that?
3 times 5.
3 times 5? So you went, instead of to 97, which would have been like, say, here, right? Would have been to 97. There's this 3 also. I'm going to change the 97 to here, and 3. So then you had to take this back off. Okay. And what's your name? Say it again.
Karthik.
Can we play ESP again? Yeah? What do you think he was paying attention to in order to use this strategy?
I think 100 is, I mean, zeros are always our friends. That's what I said. 0 is our friend.
Why is 0 our friend?
Because it's easier. Like you.
Why is it easier?
It's anything if you're adding, you're multiplying, you're doing anything. It's like, you don't, because kids normally, they get first rattled looking at a bigger number if it has multiple zeros. So if you take out the zeros, you just place the zeros, it has no value. It's not going to change the value of the number which you're getting. So it's easier to think in zeros.
So I'll tell you the reason why is because zeros are multiples of 10, and we live in a base 10 world. And so we can temporarily ignore the zeros and focus in and then recompensate. So, but we weren't talking about 1, we were talking about 100. So our answer isn't in the ones, it's in the hundreds. So we can play with that because we live in that base 10 system. That's actually the structure of our number system. So when we work with tens and hundreds, we're leveraging the structure of our base 10 number system. So he noticed that it was close to that 100, which is helpful. What was the same and what was different between the two? I have no idea where that is. The two strategies. What was the same and what was the different? And what was different between the two strategies? You can see the 97 times 5 up there. 90 plus 7. So talk at your tables. What was the same and what was the different? And what was different? All over the room, here's what I heard. It's kind of the same because they broke the numbers apart into friendly numbers, except one of them added and one of them subtracted. So those friendly numbers are like the friendly shapes. If we can build it out to a friendly shape, maybe think of this, I think one of our friends here talked about a square with missing parts. So we can add it out and then take off what we added on, or subtract it. So build it out and then compensate back, or break it apart and calculate its chunks. In both cases, we change the form of the 97. And changing form is one of the things we look to do when we're looking for structure. And in both cases, we use the same property to do it. So these are both examples of distributive property. So in order for students to think productively as mathematicians, a major shift will take place. Instead of asking what's the topic for the next lesson, unit, or grade, students will ask themselves, how can this math be extended and applied in a new domain? How does what I learned today connect to the math I've been learning, and how's it going to connect to what I'm going to learn? And in addition, kids are going to be thinking in these ways, these structural thinking. That was only one of the math practices. We decided to focus super tightly in one math practice because, well, even that's ambitious in a short amount of time, and we could spend days on this math practice in particular, but all of them together. So we talked specifically about this math practice, and we talked about the mathematical thinking that sits at the heart of all that we learn in mathematics, and talked about ways that we learn, those ways mathematicians learn, ways students learn how to think like mathematicians. And there were 3 parts of it. Name it, apply it. Name it, practice it, and apply it. So I want you guys to take a minute and go back through the mathematics that we did, the dot problem, the addition, subtraction, multiplication, all of the math that we did, and see if you can name the structural thinking that we teased out today. And I'm going to give you 3 words to help you name it, okay? You want to charge it up? Sure.
They're secret words.
Can anyone predict them?
Can anybody predict what I'm going to write?
I heard one. Say it again. Chunk.
Decompose.
Ooh, decompose. Do you mean?
Yeah, you split 100.
Uh-huh.
If you could
I heard
spell
someone say
decompose with a
change.
C, how would you spell it?
Change, someone said. So decomposing is one way to change it. And another one? Connect. Woo.
Connect.
Chunk, change, connect. So Grace did not cover any of the mathematics you guys inspired tonight. See if you can go back and look for examples of chunking complicated objects into simpler ones, changing the form of an object, a number, an expression, a shape, or connecting to another content or mathematical idea. So I'm going to give you about a minute on your own. We're going to get as many examples out in the room as we can. A minute on your own, and then we'll talk at your tables.
All right.
Share them out.
Who's got a great example of chunking a complicated object into something easier to work with, changing the form of something, or making a connection? Bueller?
Yeah, so chunking, right? So taking the blocks of 3x4. That's chunking.
Yeah, so this complicated dot pattern and chunking it into the 2 3x4s and the leftovers. Yep, taking that complicated shape and chunking it into pieces that are easier to work with. Yeah. How about changing the form of something to make it easier to work with? Examples of that?
That's the one which is behind you.
Here?
Both, you're changing forms.
Yeah, so thinking of changing the form of 97, thinking of it in terms of 100 minus 3.
Or 90 plus 7.
Or changing the form of 97, thinking of it as 90 plus 7. So changing numbers, changing shapes. Yep, makes it easier to work with. Yep. How about mathematical connections? Meaning, what math did you connect to help you calculate quicker, easier? Yeah. Yeah?
Oh, so like when you do problem where you can either subtract like the money one, you can either subtract the amount from the amount you do, or you can either add.
Yeah, so connecting, did y'all hear that? So when you bought something for $3 and you bought something for $2.73, you handed them $3 bills, you can either think of that as subtracting off the change or adding up. So connecting addition to subtraction and knowing how they relate to each other as inverse operations. Yes.
I also say connecting as addition and multiplication.
Yeah.
Multiplication is actually repeated addition.
That's right. So I could look at this as 3 plus 3 plus 3 plus 3, or I could think of it as 4 times 3. I could count that collection of dots more quickly. Or I could connect this collection of dots, this array, to the idea of area. And what I'm really determining here is the area, but instead of doing it in terms of square units, I'm doing it in terms of dots. In my head, I'm thinking about it like area because it's behaving the same way.
So for the chunking, I just want to run it by you. Like, I think chunking is a lot more than just this. How about the word problems? Because that is a major issue for most kids. But that's chunking too. The way we try is like, if there is a word problem, normally they will just get scared looking at the word problem.
Yeah.
So the information there is to read it, abstract the information what you have, and then look for the information which you need.
Yes.
So that is chunking too.
Yes, in a way. Yes.
In a way, right?
And what you're doing often in a word problem is what you're looking for. Oh, that's not flashing. Can you put that word problem back up? Yeah, that one. So if you were reading that as a word problem, one of the things that kids often do is they read for numbers. So they circle $2.73, they circle $3. And then they look for keywords that might suggest to them an operation. So like how much? Oh, maybe addition. I've got two numbers. It's asking me how much. I'm probably going to put them together. And I think what we want to do, and this sits in actually math practice 2, reason abstractly and quantitatively, is teach kids not to stop at the number and the key word, but to think about what are the quantities that are sitting underneath that number. So the amount of money the object cost, the amount of money I paid, the amount of change I get back. So the number of things, the amount of things, like reading underneath the numbers. Just like they learn. That's a topic for another day. Maybe we'll come back again and do math practice 2, reading quantitatively. But you're absolutely right. So part of this is, we're going here. Great. Part of this is where I get to dance, but I got to go this way. So often in math class, this doesn't happen in AB, you start with the answer, kids work on something, and we pull it back together, okay, what answer did you get? That's not enough. Because you could say, well, what did you do to get that answer? I got 27. The way I got it was I thought of it as quarters, and I added. But then we could push them, and teachers in this district do push kids even further. Not just how did you get it, but why did you do what you did? Why does it make sense? And that's really great to be sitting back here in the why. We're going to argue you want to even go back further to what did you even notice to begin with? What did you think was important to even pay attention to that got you thinking that this might be a good strategy, that had you do those steps that got you that answer? It's all the way back here behind why you did what you did in the very beginning stages that the mathematical thinking sits. It's training your eye to know what to pay attention to. We think of it often as helping kids know what to pay attention to. What did you notice? And then what are those questions you ask yourself when you're problem solving? Ooh, I noticed squares. I wonder if I could use squares to count quickly. How could I chunk this shape to make it more friendly? How could I change the form of it to make it work for me? So it sits, the mathematical thinking when we're teaching it sits back in the what do you notice and those questions you ask yourself. They get you to the strategy, that get you to the answer.
And it's through those noticings and the questions you ask yourself that you begin to see those connections that we've been talking about. Our vision, it's kind of hokey, but our vision for your students as they develop the math practices and start to think and see mathematics as interconnected and doable with effort, is that their brains start to look like that, with synapses firing and neurons connecting and the pathways open between ideas, between and among ideas, rather than these isolated silos in their head that 4th grade math was decimals and 2nd grade math was subtraction. It's the ways of thinking that were developed that they lead with that allow them to make those connections.
And it's not just because it makes math seem sensible and doable and connected, but it goes back to that beginning quote where we started, right? The technologies that are going to create the problems that our kids are going to have to solve haven't even been invented yet. So kids need to learn how to look at something that's completely new and different and make connections back to what they know. Think about what's important about this new thing I'm looking at. Ask themselves questions that have them chunking, changing, connecting, and working on something.
So we'll hang. If you guys have questions, we're more than happy to answer them, but we also want to be respectful, so if you need to head out, please feel free to head out.
Thank you.
Oh, wait, we have homework.
We do, we have homework, yes.
So, when you go home,
yes,
try this out with your children. Try to contemplate and calculate whatever mathematics they're doing. Sit on your hands, put your pencil down, whatever it takes, put the problem way away, contemplate what you notice first, because it's not just on our teachers' shoulders, it's also on our shoulders as parents. So, go try it out. Fun.
Yes, thank you.